Hello and welcome to our video lecture on relations and functions. Relations and functions are extremely important concepts in mathematics, and we'll be using them from this point forward in all the mathematics classes that you will take. A relation is any set of ordered pairs. A function is a special kind of relation for which every first coordinate is paired with only one second coordinate. So every function is also a relation, but not every relation is a function. So we'll see exactly what that means through some examples in a minute, but just to give you an introduction, this is basically the difference between the two. In the context of relations and functions, the first coordinate of each ordered pair is called an input, and the second coordinate of a given ordered pair is referred to as the output. So both relations and functions are sets, which we have already studied, composed of input-output pairs. If you remember, a set is nothing but a well-defined collection of objects. And the pairs will have the form input comma output. So the first coordinate will always be reserved for the input of a relation or function, and the second coordinate will be reserved for the output. When it comes to letters, we usually reserve the letter X for inputs and the letter Y for outputs. There are no restrictions on either the inputs or the outputs for a relation, but functions are more restricted in that no input should be paired with more than one output. A few examples will make this very clear. Here we'll look at an example of a relation which is not a function, given that input A is paired with two different outputs, namely 1 and 2. There's a beautiful kind of a diagram called an arrow diagram, which is very visual and intuitive, and it really depicts the relation or the function in a very clear fashion. Notice that we can see that input A is paired with these two different outputs. So therefore, this relation is not a function. Of course, it is a relation, but it is not a function. Remember, we don't have any restrictions on a relation except that they should just be some ordered pairs, right, which we have here. So we know that input A is associated with two distinct outputs, and the key word here is distinct. Note that the following relation is a function. You may be thinking, hey, the A is occurring twice, right? So why is it still a function? Because look, the key word is that it's not a function only if these two outputs are different. But remember, with sets, repetition is redundant. So in other words, this can be written as this set of ordered pairs. Just like that. So in other words, this set and this set are the same, because remember, repeats do not mean anything when it comes to definition of sets. So you should always eliminate any repeated elements in a set for a clean representation of the set. Here is another relation. Notice this time A goes to 1, B goes to 2. And you can see that this is nothing but the arrow diagram for the same relation R2 with this simplified version of it. Notice A is being sent to 1, B is being sent to 2. So if you were to do the arrow diagram for this relation, you would do exactly the same. You would never depict the same input-output pair more than once, you see? So you would still show that A goes to 1 and B goes to 2. the fact that a goes to 1 has already been stated, so you would not repeat that. You wouldn't do a new line with a goes to 1, see? So you never repeat in that manner. And so therefore, the keyword is distinct. But here we have the element a going to two different. Distinct in mathematics basically means different, okay? And that's why this is not a function. Now here we'll look at an example of a relation which is a function, given that no input is paired with more than one distinct output. Notice you have three inputs, A, B, and C, and three distinct outputs, 1, 2, and 3. Now here's the arrow diagram for F1 on the left here. A is being paired with 1, B is being paired with 2, C is being paired with 3. We'll learn in a later lesson that F1 is actually, even as a function, is kind of special, because not only does each input have one output, one unique output, notice that no two inputs have the same output either. And that's not a violation of the definition of a function, but that's not what happens here either. In other words, what we call this kind of a unique function, where each input does have an output and no two inputs have the same output, we call it one-to-one. But much more on that later. Now, do notice that for a given function, there is no problem if two or more inputs have the same output. We never said that two or more inputs cannot have the same output. All we said was that no input should have more than one output. So look at this particular relation here. All three inputs are going to the same output, but this is still very much a function, because if you were to write it out, you would see that no input is paired with more than one output. See, A is only paired with one output, B is only paired with one output, and so is C. So this is a function. In fact, this is also a special kind of a function. When all inputs of a function have the same output, what we call that is a constant function, because its output never changes. So we call this a constant function. Next, we'll look at the important concepts of domain and range. For both relations and functions, we call the set of all the inputs the domain and of the relation or the function, and we call the set of all the outputs of the relation or the function the range of the relation or function. Let's find some domains and ranges of a few relations and functions here. So here R1, we look at it. First we'll determine the type. Notice that A is being paired with two different outputs. So we know that this is a relation, but we also know that it's not a function, right? Now, the domain is just the set of all the inputs, right? So what are they? Well, we have A, and B. And remember, we don't repeat when we form a set. So we're only going to write A once and then B. Those are the only unique inputs. And what are the outputs of this function? Well, we have 1, 2, and 3. That's where we put in here. So the domain, well, I believe I said function, it's actually a relation, right? So the domain of this relation is the set containing A and B, and the range of this relation, which is not a function, is 1, 2, and 3. The set containing 1, 2, and 3. How about this one? A is being sent to 1, B is being sent to 2, A is being sent to 1 again. So if you recall, this is the one that kind of looks like it may not be a function, but it actually is. We've already seen these examples. We just want to write their domains and ranges now. So this, as you know, it is a relation and a function, because no input is paired with more than one output. So the domain of this relation and function, it's both, is just going to be A and B, and the outputs, the set of outputs, the range is just going to have 1 and 2 in it. That's it. We don't repeat the 1. How about this one? A is going to 1, B is going to 2, C is going to 3. So yeah, this is definitely a relation and a function because no input has more than one output, and the domain is going to contain the elements A, B, and C in it, just like that. And the range is going to have the elements 1, 2, and 3 in it. There's the range. Here we have another relation. A is going to 1, B is going to 1, C is going to 1. Remember, this is a constant function. It is a function because no input is paired with more than one output, and all inputs have the same output. That's exactly what we call a constant function. So the domain of this constant function has the elements A, B, and C in it, just like that. And the range has the element 1 in it. That's it, a single element in the range. That's the telltale sign of all constant functions. Their range is always composed of just one unique element. There is one other notation that we use to depict functions, and that's called functional notation. Consider this simple function we've seen before that sends A to 1, B to 2, and C to 3, right? We use the following notation to show the relationships between inputs and outputs of this function f. We say that we write f with parentheses A and then equals 1. Now this is not multiplication symbol as is usually interpreted as. In this context, in the context of functions and relations, this is read f of A is 1. That's how you read that. You say f of A is 1. So basically what you're saying is that the output of this function is 1 when the input is A. So when for this function, the output is 2 when the input is B. The output is 3 when the input is C. So f of C is the output of the function f for input C. Even though the notation f of x may be interpreted as f times x, it's very, very important to realize that that is not what is indicated when you write it in this context, in the context of functions. Here it's just an output for a given input, and you don't say f times C or f times B or f times A. You say f of A, f of B, f of C, etc. One way to visualize functions very intuitively and quickly get a feel for what a function is trying to depict and to represent is using what's called a graph. Most of the functions we'll be using in mathematics classes have numerical domains and numerical ranges. Given that functions are sets of ordered pairs, they lend themselves well to being represented in the familiar Cartesian coordinate system. We use the x-axis as the input or independent variable axis, and the y-axis as the output or dependent variable axis to plot a function as a set of ordered pairs of the form input output equals xy. So in this context, we reserve the letter x for inputs and we reserve the letter y to represent outputs. All right, so let's say we want to graph this relation depicted here in the Cartesian coordinate system. Remember, we're going to use the familiar x, y axis, the Cartesian coordinate system, which is basically composed of a pair of perpendicular real number lines, and then we'll just plot these points, right? Remember, these here are not intervals. I know this can be a little confusing when you go back and forth between what this notation meaning intervals and then meaning ordered pairs. But you know, as you get more and more comfortable with this stuff, it'll be no problem going back and forth, and it'll always be completely clear from context what is indicated. So here we're plotting the ordered pair 0 0, which is of course right there. Then 1 3 is right there. 2 6, right? And 3 9. That's it. So we just plot those points and we have graphed this particular simple function which has a finite domain and finite range, which we will specify here now. Remember, domain is the set of all the inputs, right? So what are they? 0, 1, 2, and 3. The range is the set of all the outputs, so 0, 3, 6, 9. So what if I say what is f of 2? That just means what is the output of this function when the input is 2. So here's the input. What's the corresponding output? Right there. So f of 2 equals 6, just like that. Now, another question that could be asked is, for what value of x does f of x equal 9? So this time they're giving you the output and they're asking you to find the input that would have that output, right? That would be paired with that output, right? So what we need to do now is we need to locate the y value 9 and then see what x value it's paired with. So here the answer would be x equals 3, just like that. So very simple, very important. Please make sure you understand it before we proceed. Sometimes we're given the graph and we're asked to write the relation or function using the graph. So here we notice that each of these larger tick marks is broken into 4 equal parts, so each is half a unit, right? So this right here would be 1 unit, right? And so would this represent 1 unit. So this ordered pair here is 1 1. That's the easiest way to go about this. First write down the ordered pairs, then we'll proceed. Notice that this here would be 3, so that means this point corresponds to ordered pair 1 3. This point here is easy, that's just going to be ordered pair 2 2. And this one here, notice here the x value is 3 and the y value there is 4, so this is the ordered pair 3 4. Okay, so here we're just going to write those ordered pairs as the definition of our relation. Now this is a relation and it is not a function. Think about why that is for a minute. Pause the video and do 2 things. Think of why it is that this is not a function. Of course it's a relation. Any set of ordered pairs is a relation. So find out, see if you can tell me why this is not a function, and also come up with the domain and range and answer these questions. Then come back. Alright, so I'm sure you realize that it is not a function because the input 1 is paired with more than one output. 1 and 3 are different, so it's paired with more than one distinct output, right? So it's only a relation, it is not a function. What is the domain? Well, remember, that's going to be the set of all the unique inputs, right? So basically 1, we don't need to write it again because we've already got it. 2 and 3. And the range is the set of all the outputs. So notice we have 1, 3, 2, 4. Could I have written it as 1, 2, 3, 4? Would that be okay? Absolutely. Sets are not ordered, right? So these are the same set. What is f of 2? In other words, what's the output of this relation when the input is 2? Well, here's the input 2. We know the output is 2. Now, don't be confused by the fact that f is used here. Remember, these are just names. It doesn't matter. Understand the concepts behind what is going on here. So we say f of 2 is 2. For what value of x does f of x equal 3? Well, we need to know this when 3 is the output, meaning in the y position, right? What input is it associated with? And you can see here, it's what? X equals 1. Now, it is true that we will usually use the letter f with functions, but sometimes, you know, it may be used in the context of a relation. It very rarely so, but don't get attached to the letters. Try to understand the concepts. Now, we just looked at a couple of different problems on the previous page, and we'll see, we're going to look at the graphs again and realize there's a really important difference between them. Notice that if I consider all possible vertical lines, right, none of them would cross the graph of this particular one on the left, which was a function more than once, right? But notice, because with this relation, which was not a function, the same input or x value was paired with two different outputs or y values, there is a vertical line that would cross the graph of this relation more than once. And this is precisely what brings us to this very important concept called the vertical line test, because this failure will always happen with every relation, because every relation will have at least one input that's paired with more than one output. Now, remember, you may have many points that a single vertical line goes through, but it doesn't matter to us, because all we need is one with more than one point of the relation that is contained in it. So one vertical line, and that's how you know this graph is not a function, the graph of a function, and this graph is the graph of a function, because no vertical line would cross this more than once. The formal statement of the vertical line test says if no vertical line crosses the graph of a relation more than once, then the relation is a function. The vertical line test lets us tell whether a graph represents a function or not instantaneously. That's why it's so powerful. This will play a particularly important role when we look at functions with infinite domains and or infinite ranges, which we will look at next, and which are extremely common in mathematics. In fact, most of the relations and functions we will be encountering in this as well as future math courses, classes, will be defined based on a relationship between the input variable, also known as the independent variable, and usually represented using the variable x, and the output variable, also known as the dependent variable, and usually represented using the variable y. And not only that, but most of the functions that we will study will have infinitely many input elements as well as infinitely many output elements. So we graph these relations and functions using the Cartesian coordinate system, and we will let the input variable values be depicted using x values and the output ones using y values. So each point on the graph of a relation or function will have the form input output. Now, to see how a function may have an infinite domain and a range, remember this example that we saw earlier, right? Here is the definition of the function. Do you see a pattern? Can you come up with a formula that would define each of these y coordinates in terms of the associated x coordinate? Think about that for a minute before we proceed to the next page. Notice that in this example, we've restricted the domain of this function to just 4 inputs and 4 outputs. And unless we have a reason to do this, we usually do not form this restriction. What we do is we actually expand the domain to all real numbers, which actually would expand the range to all real numbers as well in this case. Now, if you notice, each output element has a relationship to the corresponding input element. Did you find out what that is? In fact, each output is 3 times the corresponding input, isn't it? So for a general output x, we can say that the output is 3 times x, right? And notice that we can say y for a general ordered pair xy, right? If I were to use a general ordered pair xy, I would say y equals 3x, right? Now, if I simply take the y and replace it with f of x, I have depicted this function using functional notation right there. So f of x equals 3x. We can, of course, write y equals f of x equals 3x, and notice that the domain will be all real numbers, because basically the domain is the set of all allowable inputs, right? There is no number, a real number, that would get us into any kind of trouble if we tripled it. So the domain can be any real number, and the range will also turn out to be all real numbers. In fact, you should recognize this as a linear function, because we have studied linear functions before, and this is basically nothing but a simple linear function whose graph can easily be obtained. All right, so here we have actually graphed the linear function y equals 3x, or f of x equals 3x, and notice we have shown several input-output pairs here, not just, you know, perfect ones like 0, 0, 1, 3, 2, 6, etc., which we had seen before. Here, for example, we have pi, and this is 3 pi. Try it. Multiply pi by 3, you'll see you get something approximately around 9.42. And also, you know, of course, we can have negative inputs, and in this case, which will result in negative outputs as well. Remember, again, the relationship is each output is 3 times the corresponding input. All right, so here is a graph of that particular linear function. Now, we can do what's called a functional evaluation using the functional notation. Notice it's very simple, because we just say, if we want to know what is the output of f when the input is -2, all we have to do is plug in -2 instead of x in the definition of the function. So we get 3 times -2, which is -6. If we want to know what is the output of the function when the input is negative 2/3, we'll do the same thing. We'll multiply 3 by x, which is negative 2/3, and of course we get negative 2. Same thing goes with all these other inputs as well, regardless of whether they're rational or irrational, simple or more complicated. Anyway, so f of 1.5 equals 3 times 1.5, which is 4.5. F of pi is going to be 3 times pi, which we can just leave as 3 pi. Or as we saw on the other screen, we can actually substitute and get something around 9.42, etc. One really useful way of imagining a function is as a machine. Basically, a function is a machine. You feed it an input, out comes an output on the other side. Now remember, no input can have more than one output, but more than one input may have the same output. So for a summary of the ways we can represent functions, remember, the machine demonstration is only for visualization purposes, right? It's not actually a method we use for depicting functions, but the main methods are we can use the actual set of ordered pairs like we have seen, or we can use the arrow diagram, right? Put the inputs and the corresponding outputs, right? Using arrows, or we could use a graph, right? Or we could use a rule such as f of x equals 3x, right? So these are all different ways you may see functions depicted in mathematics or in other fields where mathematics is applied. For our next example, we're going to look at a given relation, determine if it's a function, state the domain and the range, regardless of whether it's a function or a relation, and then see if we can see a pattern. If so, we'll write an expression for it, and then we'll find f of 2 and also find the value of x for which f of x is 1. So let's start by determining whether it's a relation or a function. Notice that each input is associated with only one output, right? There is no repeat of any of the inputs, so we don't need to worry about an input going to more than one output. So we know this is in fact a function. Well, of course it's a relation too, but it's a relation that is also a function. The domain is simple, of course. That's going to be the set of all the inputs, so 0, 1, 2, and 3. Anytime you know how to do these, you should try to stop the video, pause the video, and do it on your own, and then come and compare answers. That's the optimal way to go, as you know. State the range. The range is going to be the set of all the outputs, 1, 3, 5, and 7. All right, do we see a pattern? Now, you have to think about this one a little bit. It's not as simple as the last one, but it's not that much more difficult either. See if you can find the pattern, pause the video, and then come back. All right, so you probably noticed that if you double each input, you almost reach the output, right? But you would have to do what? Add a 1, right? So it looks like f of x for a given input x, general input x, should be double that x value, but add 1. Let's see if it works. What's twice 0? That's just 0 plus 1 is 1. What's twice 1? That's 2 plus 1 will give you 3. Twice 2, that's 4, plus 1 will give you 5. Twice 3, that's 6, plus 1 gives us 7. So this would be a depiction of the generalized function f of x here. Now if we want f of 2, we can either just look here and go, okay, that's just the output of this function when the input is 2, so it should be 5, right? Notice we could also use this definition we came up with to figure out f of 2, because now we're just going to substitute 2 for x, so we get 2 times 2 plus 1, which is also 5, just like that. Okay, so there's more than one way we could handle that. Also find the x value for which f of x equals 1. Now we're going to be looking at output being 1. So we're going to look for the y value, which is 1, and see which x value is associated with it. And of course we can see that should be x equals 0. Could we have used this definition to find it? Well, let's find out. Remember, this time we're going to replace f of x with 1. So we get 1 equals 2x plus 1. Now we're going to go ahead and solve for x. So we get 0 equals 2x. Now we're going to divide both sides by 2. So we end up with x equals 0. So we could do it using just these ordered pairs, or we could use this function functional definition to do it. Notice that it's always good to be able to do it in this manner, because what if they ask you for an output that happens not to be depicted for a function with infinite domain and infinite range, right? That's when this technique is going to be invaluable, right? You have to know it. All right, so here we're given a relation which is depicted here to the right, and we want to know if the relation is a function. Notice that the simplest way to do that is by using the vertical line test, and of course using the vertical line test would be easy here, because you can already see from the grid there are several vertical lines that cross this graph more than once. So this is definitely not a function, right? What about the domain? What is the domain of this relation? Well, the domain is the set of all the x values, right? So one way of thinking about it is, if I were to take each of these points on this graph and decompose it. What I mean is, if I find out what x value it is associated with and what y value it is associated with, right? Then I do that for every single point, right? And let's say that I use the color red for the x values, right? So notice this one will come from here, this point will come from here, this point will come from here, etc. I'm just doing some sample points, right? So if you were to paint the x-axis with red for each input, right? And let's say we use green for the outputs, so you can see this one comes from here, this point is associated with that y value, this one with this one, etc. Right? So this one comes from this y value, this one comes from this y value, this one comes from this y value, and on, right? Notice, what would you see painted in red after you did that? Let's say you have an infinite amount of time and you do this for every single point on this graph, right? You would eventually see the entire positive x-axis painted, right? Well, I should say non-negative x-axis, because 0 is going to be painted too, because that's going to be one of the outputs actually it's going to be painted with green and red, but I'm particularly interested in red right now because we're asking the domain first, right? So the domain is going to be basically all real numbers greater than or equal to 0. So bracket 0 comma infinity. The range, which is the set of all the outputs, notice we get all the real numbers this way, because even if it's a very large y value, remember this is going to go on forever, right? So eventually it'll get high enough to where you'll hit every y value on the y-axis, and the same down here. Eventually this will go low enough to where you'll hit every negative y value as well for the set of outputs. So the range is in fact all real numbers, like so. All right, so that's how you take a function or relation and find its domain and range if they happen to be infinite in the size. Okay, here we have another graph. We want to first determine if it's a function, if the graph is depicting a relation that's also a function. Remember, we do the vertical line test, and if no vertical line would cross this more than once, then it would be a function. And notice this does pass the vertical line test, right? So this is definitely a function. The domain is the set of all the inputs or the x values. Remember, if we take each point and see what x value it is associated with, right? This one would be associated with this x value, this one with this one. We're just doing some sample points, right? This point would just come from right there. This one would come from here. This one would be associated with this point, that point. This one would be associated with that. We can do the same, of course, with the for each point with the y values. This point came from this one and it comes from this y value, right? So we're just, this point would be associated with that y value, right? This one here, this one comes from that y value, etc. So of course, for each point there's an x value and a y value, right? You can decompose each point separately, or we can just do different y and different x values just to get a feel for what all the set of all the inputs will look like and the set of all the outputs will look like. Notice that eventually, if we did this, if we had enough time and did this for every point on this graph, the entire x-axis would become painted red, right, with inputs. So the domain of this function is actually this time all real numbers. And the range, on the other hand, here is what's limited. Notice you don't get any outputs down here. So the outputs, or the y values for the ordered pairs, right, x, y, all the y values are going to come from here and up, right? So basically the range is going to be bracket 0 infinity. Now this one is actually, if you were to write it in set builder notation, be careful, you'd want to say all y such that y is greater than or equal to 0, like so. All right, so we're going to use this graph to find f of 1, right? So we want to know what's the output when the input is 1. So what we do is we go to 1 on the x-axis, right? And we go up till we hit the graph, and then we go left till we hit the y-axis. And there we can see that the output is also 1. So what is f of 1? F of 1 is 1. Now we want to use the same graph to find f of negative 1. So remember, this time we're going to go here, negative 1. We go up till we hit the graph straight up, and then we go to the right to see what y value is associated with it. And we can see that one is also 1. So remember that what kind of functions have the quality that each input has an output and no two inputs have the same output, see? So this one is a function, right? Because it passes the vertical line test. But notice, because -1 and 1 both are being mapped onto 1, we say that the function is not one-to-one. So yes, it is a function, but it is not one-to-one. All right, take a moment, see if you can answer these questions and then come back to the video. All right, welcome back. So here we have a relation that's depicted. We want to determine if it is a function. You have to, this takes a little bit of imagination, because you have to imagine all possible vertical lines, right? Crossing it. Would any of them cross it more than once? As you have probably guessed, that's not the case. They don't, right? Now, remember our last graph? This is actually a what we call a quadratic or second degree graph, right? When you have a simple linear function such as f of x equals 3x, which we've already seen, the graph is a nice straight line, right? If you remember. But once you get higher powers of x, the graph kind of bends. It's not going to be just a straight line anymore, right? So this is like a quadratic graph. This one here is actually a cubic graph. This is the graph of f of x equals x cubed. On the previous page, that was the graph of f of x equals x squared, right? Etc. These are all very well behaved functions called polynomial functions. So it is a function. What is the domain? Now remember, you're going to sit in some spaceship and you're going to shoot, and from each point you're going to shoot a red dot at the x-axis where it comes from, and you're going to shoot a green dot at the, oops, that's red, at the y-axis where the point comes from. Again, go to another point, you're going to shoot a red dot at the on the x-axis where the point comes from, and a green dot on the y-axis, etc. So if you were to do this for each point, right? Notice, by the way, 0 would be both, the origin here would be both red and green, right? And then, for example, this point comes from this x-axis, and this y value, this x value, and this y value. Let's pick a few more points. Let's say we pick this point, right? Notice this point will come from this x-axis and from this y-axis, etc. So notice that if we took long enough to do this, you would realize that all real numbers are in play when it comes to the inputs of this function, and all real numbers are also in play when it comes to the outputs of this function. So in this case, both the domain and range of this function are the set of real numbers. Which will depict as an interval from -infinity to infinity. Like so. All right, so here is another graph, and it was a function, and there's the domain and range. All right, next we want to look at a relationship defined by this rule right here and determine if it's a function or not, and then state the domain. So we noticed that basically every input x, such as, for example, if we make a table of values, this will make a lot of sense. Notice that, for example, if I plug in 0, I'm going to get 2 times 0, which is 0 plus 1, which is 1, right? If I plug in another input, such as 1, I'm going to get 2 times 1 plus 1, which is 3. etc., right? Notice that there's no way 0 is going to end up giving me any other kind of output, right? Or 1, etc. When you take any x value, double it and add 1, you're just going to get one y value, right? So this is definitely a function. We can even take a look at its graph real quickly and see that it easily passes the vertical line test. Of course, we've graphed lines before, so we'll take a look at that now. So notice here we have the graph of y equals 2x plus 1. And of course, it easily passes the vertical line test. Notice that all x values can be used as inputs, so the domain is all real numbers. In fact, if you look at all the resulting outputs, you will notice that the range will also be all real numbers. In fact, this holds for all oblique lines, right? Notice that for all oblique lines, no matter what they look like, or if they have a positive slope or a negative slope, etc., they will all pass the vertical line test, and they will also have all reals as their domain and all reals as their range. There are two kinds of lines that behave differently. One is vertical lines. Notice that those are not even functions, right? Take a look at the y-axis itself, right? Remember, the y-axis as a graph would fail the vertical line test miserably, right? Because there's one line, namely itself, that would cross it many, many times. In fact, infinitely many times. So vertical lines do not represent functions. Horizontal lines, on the other hand, do represent functions, but they're constant functions. So the range would be a single element. It would not be the set of real numbers. So back to our example, we did realize that yes, it's definitely a function, and the domain is all real numbers. And as we saw on the other page, the range is also all real numbers. All right, so we're going to look at a slightly different rule to see if this rule defines a function as well. This is quite different though, even though this seems very similar to the previous one. That one was y equals 2x plus 1. This is y greater than 2x plus 1. So here, if I take a single input, such as let's say 0 for simplicity, notice that 2 times 0 plus 1 will give me 2 times 0 is 0 plus 1, which is 1. Notice that if I pair that with, say, 2, then we can see that the ordered pair 1, 2 satisfies this relation. What if I take 1? It's also less than 3. That means the ordered pair 1, 3 also satisfies this relation. Notice 1 is also less than 4, so I can easily see that 1, 4 also satisfies this relation. So notice that the same element 1 is paired with 2, with 3, with 4, etc. This definitely violates the requirements of a function, so this is not a function. However, as far as the domain is concerned, notice that any x value can be substituted for x here, so without causing any kind of error or anything like that. So therefore, the domain would include all real numbers, like so. So we have come to our last example here. We want to see if the relation described by this rule is actually defining a function. And what you have to keep in mind is that x is always associated with the input and y with the output of relations and functions. So in that sense, if there is some way we could come up with two different y values that are corresponding to the same x value, that would be a very quick way of showing that this is actually not a function. So we do notice that if we take, for example, -1 and use it for y, that implies x is going to be the square of -1, which is 1. And what if we were to use 1 for y? Notice x is going to be the square of 1, which is also 1. So now, if you look at those in a table, we just showed that 1 as the x value 1 is associated with y value -1, and it's also associated with y value 1, right? So in other words, if we do an arrow diagram, we can see 1 is associated with both -1 and 1. So again, here, this would not be a function. All right, as far as the domain, remember the domain is the set of all the x values, right? And since x is the square of y, notice that regardless of the y value, the x value is never going to become negative. The worst case scenario is that it may become 0. For example, when y is 0, notice that x is going to be 0 squared, which is 0. So, but if you plug in any other value for y, you're definitely going to get a positive value for x. For example, let's do a few more values. Notice that if y is -5, for example, x will be the square of -5, which is 25. If it's say -2/3, y is going to be the square of that, which is 4/9, right? And of course, positive values like 5 will also give you a positive result, and for x, and 2/3 will also give you a positive result. So on this side, on the x column, you're never going to get a negative value, but you will get all possible positive values plus 0, right? In other words, all non-negative values. So the domain here will be bracket 0, infinity. Later on in the course, we'll realize this is actually a what's called a horizontal parabola, and we will learn a lot more information about it than we are currently learning. But this is a really great introduction to them, and it'll make a lot more sense when we see them again later on. And that should do it for our discussion of the very important topics of functions and relations. So please practice on the homework, and I will see you at the next video. Stay safe.